Okay, thank you. Hi everyone. So I'm going to talk about extractive summarization because we want to focus on other evaluation metrics than Rouge, and especially on automatic pyramid. So we start with the task of extractive multi-document summarization, which is simply extracting a set of sentences from the source document. And this can classically be thought as a discrete budgeted optimization problem, which means that we are looking for a set of sentences which maximizes some objective function that we might call theta under some length constraint. And the question is how can we choose this objective function? And usually this objective function will follow or will be influenced by the choice that we make for the evaluation function. So typically, it's very common to use Rouge as an evaluation because it's very simple. It's simply the n-gram overlap between the reference summaries that have been written by humans and the system summary. And it also has good correlation with humans, so it became standard, but it is also criticized and it has some weaknesses. So the one that we are particularly interested in this work is the fact that lexical overlap does not necessarily mean semantic similarity. So there can be some lexical overlap without meaning the same, without having the same meaning, and we can express also the same meaning without lexical overlap. So in this work, we would like to investigate alternative metrics. So alternative to Rouge, both for the evaluation and also when we design the system. So which evaluation metrics do we have in mind when it comes to designing the system? So in the ideal case, we would like to use human evaluation. So one way of doing human evaluation for content selection would be the so-called pyramid, which is a way of annotating content selection with a high inter-annotator agreement. The problem is that pyramid is manual, so it's expensive and it's not reproducible. But recently there was some work that have been trying to automate this process of pyramid. So one that we will use in this work was so-called Peak, which was developed last year, and it automates the process of pyramid by replacing the component that needs human annotation by state-of-the-art NLP components, and we will use it both for the evaluation and also for developing our system, which means that we will try to develop a system that optimizes toward this metric. So before starting, really get some background about the manual pyramid, what it is. So in the manual pyramid, there is this notion of the SCUs, which are semantic content units. And we start with the reference summaries, and humans define what they consider to be SCU, which means the basic pieces of information. And then there is the pyramid set, which is the set of SCU, and each SCU has a weight, which indicates in how many reference summary it appears. So for example, here we represented them with some each SCU is represented by some triple. And the red one appeared in 3 reference summaries, so it had a weight of 3. And then there is a second part. It's when the pyramid sets are already constructed, and there is a new system summary that comes in and that needs to be scored. So human annotator again read the summary, and they look at the pyramid set and they say which SCU appear in this summary, and then the final score is the sum, the average of the matched SCUs, of the weight of the matched SCUs. And so Peak automates the whole pipeline, but we would be interested only in the scoring part, which means that we assume the pyramid sets are already available to us, which is the case in several data sets, in standard data sets. And for us, it has the advantage also that we use the pyramid sets created by humans, which is we can consider them as good, and there will be less error propagation as if we use the whole Peak and the whole automated system. So to take a look at how the automatic pyramid works, it converts the SCU into propositions and the summary into a list of propositions using the OpenIE framework, which is called Close IE. And we have a set of propositions for the pyramid and the system summary, and some similarities computed between these propositions using the ADW, so aligned, disambiguate, and walk. And we draw an edge if the similarity is above a chosen threshold. And this gives us a graph, a bipartite graph. And from this graph, there is some matching algorithm, the Munkres-Kuhn algorithm, which is run to find the optimal matching. And the result is a list of summaries a list of propositions from the summary and from the pyramid set which are matched. And the score for the summary is the sum of the weights of the matched SCUs. So this is the automatic metric we want to use. And since we have this metric, we would be interested in getting its upper bound. It's getting an idea for the upper bound. So the problem is that simple integer linear programming is not possible because of the bipartite matching algorithm, and the similarity computation is time consuming. So what we do is that we pre-compute the matrix A, which contains already all the similarity between all the propositions in the source documents and in the SCUs. And we compute the upper bound approximately using some genetic algorithm that we developed last year for summarization, and using the fitness function to be peak. And it has also a nice advantage is that later we want to train our system, and the population of the genetic algorithm will be a good quality training data, because it has summaries ranging from almost random to almost upper bound, and with all their scores given to the real peak, so their scored summaries. So now if we want to get to the system, so we want to develop this function we call pi, which approximates the true peak, so pi star, without having access to the pyramid set, because at inference time we do not have access to manual or human annotations. And we look for pi in this form in order to make it linear. So I mean linear with respect to sentences. And we have two functions. So the function f, which scores individual sentences, and intuitively it represents importance, and the function g, which scores pairs of sentences, the intersection of pairs of sentences, and implicitly it represents redundancy. So we use this generated training data from the upper bound computation, and for each summary we can extract features. So we have features for sentences and for pairs of sentences, for intersection of sentences. So the features are things like typically used in summarization, like centrality, position, overlap with title. And for the pairs of sentences, this would be the unigram, bigram, or trigram overlaps. So the problem is that we will have a variable number of features because we have a variable number of sentences in a summary. So we could use RNNs, but we would lose the linearity assumption, which is useful for us because later we want to do optimization to extract the best summary, and linearity is a very nice to have for our functions. So instead we use linear models, and we look for two weight vectors W and omega that are in this way. And so we learn the W and the omega with gradient descent on our training set to approximate best peak. And then, because we enforce the linearity condition on our function pi, it's very easy to extract the best summary according to our function by simply solving the following integer linear program. And we have the length constraints. So we did some experiments. So first, with the upper bound, we used the TAC 2009 dataset because it has the pyramid annotations, and that was convenient for us to use. So we report the difference between the upper bound both with Rouge, that was computed with an integer linear programming, and with peak, which was computed with our genetic algorithm, for two different threshold values, 0.6 and 0.7 for the similarity. And we observed that there are big differences between the upper bound, which hints that the metrics actually capture different properties. So the upper bound for Rouge is not so great when measured with peak, and the upper bound for peak is not so great when measured with Rouge. And there are some other detailed analysis in the paper measuring the differences. But now for the system, so we did the same setup. So instead, since we have a supervised learning, we use the live one at cross validation for training and testing. So we compared against several traditional summarizer. I put some here, and we see that the system that we developed actually performed similarly with the previous system, slightly lower, but similarly. But it has much better scores on the peak, which is expected because it was optimized for it, but we still see a very large gap. And, but we also see that there's a lot of room for improvement when we compare to the upper bound that we just computed before. So there might be some more work here in this direction. So just to conclude, I want to give some discussions about this. So we just developed a simple model that is linear and that optimized for a different metric than Rouge, which is the automatic pyramid. It has promising results without so much loss on the Rouge, and there is a lot of room for improvement. But then we also enforce this linear constraint, which is quite a strong constraint, and by removing this constraint, we might get a much better approximation. And we also should ask the question, is peak really better than Rouge? It should also be tested on different genres and different domains. And also Rouge can deal with many languages, and at the moment this peak, it works only for English. So we still need to investigate alternative evaluation function, but I think for summarization it's quite critical to think about which function we choose for evaluation, because once we choose a function to be the evaluation function, then we will be necessarily optimizing toward this function, whether by supervised system or by repeated comparison of unsupervised system. And we would always get the weaknesses, our system will get the weaknesses of the evaluation function that we are choosing. So it's important that we think about the weaknesses of our evaluation function, and that we also try to develop system for different evaluation function, and also study the evaluation function and the impact that they have on our systems. That's it for me. Thank you.
Hi. So in place of using genetic algorithms for solving the ILP, could you relax it to LP and then round the solution?
Sorry?
Could you relax your integer linear program to a linear program,
yeah,
and then round it to solve the problem?
So there is two optimization here. There's one optimization for the upper bound computation, which we cannot do with integer linear programming, sure. So we use the genetic algorithm. And the other one, when we extract the summary, which we do with sure. ILP. So which sure. You're talking about the first one?
The genetic algorithm.
Genetic
yeah.
algorithm. So we didn't think too much about clever ways of doing it, because we had code existing that could take a function that has no mathematical property and optimize it. So the genetic algorithm does that. So, but that's true, we can really think about it, and I think it would be useful, especially if we come and remove the linearity assumption. Then we would not be able to use the integer linear programming for extracting
gradient descent in a relaxed version.
Yeah, and this kind of thing. Okay.
Hi. Sorry, I didn't get. Do you extract full sentence or segments of the?
Yeah, we extract full sentence.
Okay.
Yeah.
So when you optimize for peak, are you worried that actually you might lose on readability, like that? You know, like for example, optimizing for Rouge is dangerous because you might. So basically, it's a metric which evaluates very well human-produced summaries. But if you start to have a machine which like exactly optimize it, it might lead unnatural summaries. So did you like do some readability test or some human evaluation?
Yeah. So the thing is that since we do extractive summarization, we do not have an issue with grammaticality. We usually have issues if we extract several sentences and there is no coherence resolution or this kind of thing. But I would say it's a classical problem that we get whether we do with Rouge or with Pyramid or with anything else, if we do not think about it. And then we did some manual evaluation, but we do not report the result because the internotator agreement was not good enough to be here. And it seems that the readability is the same whether we do for Rouge or whether we do for Pyramid, which is not perfect, but it's okay.
Okay, thank you.
So there's, I think there's many very good summaries that we can consider good. And when we go and look at the upper bound, and we look at the upper bound for rouge and the upper bound for peak, and we ask humans which one they prefer, it seems that the humans prefer the one that comes from peak. And so I don't really know exactly what would be the underlying difference in what they extract. But when we look for the upper bound, but when we look at the systems, we see that the system has a better performance for peak, but a similar performance for rouge, which is an indication that we can get the same word or the same n-grams and meaning different things, because peak will get this semantic slightly better than rouge, which rouge does not get it. But they will get the same score on rouge, which means that they are getting the same bigrams or the same unigrams.
Do you know why people are preferring the summaries where you're optimizing?
No, I don't know. But I think detailed manual evaluation should be done. Also, I think in different domains, different genres, to really measure what is the impact of choosing peak or other evaluation metric versus rouge would be interesting.
I was just wondering whether it would have something to do with the fact that peak is based on this approach that it's not just the content, it's the importance of the content, and that rouge may not be capturing that.
Yeah, that's also